This will be the second day. So let me start from introducing the jurors. I am Yewon Shi from National Donghua University, and we have Professor Wei Wu from Taiwan University, and Professor Hu Qinpi from Donghua Normal University, Professor Liu Dai Ning, Professor Liu Dai Ning from Indong University, Professor Liu Xianglin from the Host University, Taiwan Normal University. Okay, so let's from the reporter, let's introduce your members.
Okay, so hi everyone, I'm the team leader of the team for the week. My name is Huang Weizhe, and here's my teammate is Chen Jianchang, Liao Li, Liu Jiachen, and Bo Zhi. So we're very honored to here to have a physics fight with everyone.
Thank you. I'm the opponent.
Hello, we are Team Miracle. My name is Lin Xian. He is Liu Zhongtao. He is Deng Renze. He is Bo Zixun. Nice to meet you guys.
Thank you. The reviewer.
Hello everyone, we are from Chenghua Senior High School and we are Crusaders. These two are my bosom friends, and also it's a great honor to have a physics competition with all of you.
Okay. So we start from the opponent challenging the problem.
We want to challenge question 13, spaghetti accelerator.
13. Okay. What do you have? 1 minute.
We accept your challenge.
Okay. Question accepted. Now, the reporter, you have 5 minutes to prepare. Yeah, and all the teams, please write down the names of the representatives.
see the PVC clearly.
For the projector,
This is like can you
the brightness,
the light right?
the brightness.
I only can use two.
Okay.
The biggest brackets.
这个能调整吗？
来，有没有好一点
Is？it better?
Yes.
Okay. You good?
Yes.
OK 吗？
Okay. Then. Go on.
Okay, hello everyone, I'm the reporter from Team Bernoulli, and today I'm going to report Pump 13 SCSI accelerator. For a pump statement, when a piece of SCSI is pushed into the tube, a small division of SCSI may be ejected from the other end of the tube at a surprisingly high speed. So I need to investigate this phenomenon. For my observation, from the video you can see that when I start to put the SCSI into a tube, the SCSI will start to bend, and when I keep pushing into the tube, at the moment the SCSI will start to break into debris and eject out at very high speed. And so as here is some of my experience of dealing with different diameter size of tube, and I also collect the debris, and I found that the length of debris is same in the same experiment. So in here, I'm assuming that each SCSI will have same breaking point in the same tube. And about my experiment setup, I use a 3D printer to print out the different size, different diameter, and other parameters of tube to do a comparison to see the different eject velocity. And also I stick a tube on the board so I can know the coordination. And also I use the slow motion and the tracker to analyze the eject velocity of the debris. About my entering method, for that one is at first I put my SCSI along the tube, but as the video you can see that the SCSI of the debris will stop in the tube, it won't eject out. And so in here I use the right way. I put the SCSI stuck on tube point for this tube point, and you can see that the SCSI will eject out very fast. So in here I will use the right way to do my experiment because it's more stable to control the debris to eject out. Next, I will talk about my qualitative eject process. First is about initial statement, just as an observation. I put a SCSI on the tube points on the debris so it will become more stable. And also, in here you can see that the SCSI in here won't keep shaking, so I can control the initial statement on these 2 points. For the next stage is about buckling. When I start to put the SCSI into a tube, the SCSI will start to bend, and it will cause a default, and this is called buckling phenomenon in here, which means that it will cause a default, and also there's energy stored in my SCSI. And about that stage, about ejection, when I put the SCSI into, keep pushing it, and when it goes through the limits, the SCSI will reject, or the debris of the SCSI will eject out, and also release the energy that's stored on the buckling. So next is going to talk about my quantitative velocity. So I need to talk about some theory about my velocity, eject velocity, and about energy. So since the bending situation of a SCSI in here, I approximately try to use the bin theory to describe the bending situation of my SCSI. So in here I can get the moment of inertia and Young modulus of SCSI, so I can know the elasticity or other features of my SCSI. And this is how I measure my Young modulus and moment of inertia. I put a weight on the middle part of the SCSI, so the SCSI will have a default. And I can use the default as my first relationship to know the Young's modulus. And so I easily use the strain energy computation to know how big energy that the spending really stored. So after knowing this, I can know this equation, so I can get the stored strain energy that is stored in this SCSI. Also, and here I assume that the strain energy will totally transfer into the kinetic energy of the debris eject velocity. So next, I'm going to talk about experience to prove my assumption and my theory. So first is about the different diameter of the SCSI. In here, I find 6 different bands of SCSI to do experiment, and with also measuring their Young's modulus, then they're very similar. But in this 6 band, I only find 2 different diameter of SCSI. It's 1.8 millimeters and 1.5 millimeters. So I will use these two different diameters to do experiment, and also use the same tube, same way to see the different velocity of ejection of these two different diameters of spaghetti. So after I put the spaghetti into a tube, I'm very curious about what's the different millimeters of different bending situation when I put the same weight on it. So in here I put the same weight on the middle point of the spaghetti. As you can see that there is significant different bending situation with these two 1.8 millimeter spaghetti and 1.5 millimeter spaghetti. So here my assumptions due to the different bending situation, I assume that you have different energy stored, so you'll have some different exchange energy, and also due to the energy transfer, you'll have some different velocity of degree ejection. Here's my result of different diameter of spaghetti. For x-axis is the diameter of my spaghetti, and for y-axis is the velocity of ejection. So as a result, you can see that with a bigger diameter 1.8 meter one, it has bigger eject velocity. For 1.5, it has smaller eject velocity. So according to my theory and my equation, I can know that the energy have some relationship between the moment of inertia, and also the moment of inertia depends on the different diameter, like the equation that I use. So here I assume that with bigger moment of inertia, you will have bigger strain energy that is stored. Also, due to energy transfer, you have much bigger energy goes to the ejection of debris. And for my next experiment involved, I change the diameter of the tube. So in here, I use a different diameter of tube. I use the 0.8, 1 and 1.2 centimeters, and also I control the same radius, which is this part. This part is 5 centimeters. I also use the same spaghetti of same diameter and same interweight, and also compare it to see the different velocity. Here's my result of different. And here's my result of different diameter of spaghetti. So as you can see that with a bigger diameter of spaghetti, a 12 millimeters one, it has much bigger eject velocity. So next, I'm going to change my different radius on my spaghetti. So in here, I use the same diameter, which is 0.8 millimeters, to do experiment. And here's my result of radius of tube. So for x-axis is a different radius, and for the biggest radius, it will have some smaller eject velocity. So you have a complete different results with the diameter of the tube. So next, in here, the next experience is about the proportion of the tube. In here, I change my radius and also my diameter in the same time. I use five different proportions to do experiments. And first is about a much bigger diameter, bigger proportion of my tube. So as you can see that when I push my spaghetti into a tube, the spaghetti will directly pass over the tube. And the spaghetti can't get to a bending limit, so it won't cause the debris, and the debris won't eject out. And for this one, it's about my different depth of spaghetti and the maximum force that the spaghetti can afford relationship. Also, I do a smaller proportion of tube. This one is for the 2 millimeters one, and my spaghetti is 1.8 millimeter. So as you can see that for a medium, when I push a spaghetti into a tube, the debris of spaghetti will stuck inside. So also, with the diameter of tube and the proportion to be bigger than spaghetti more, so that the debris will eject out. So here's my all different proportion of tube in here. I use the 3 to 11 one. So you can see that with a tube small and tube big, like 13 and 2, it can't eject out. So I will focus on the point at the middle of the part. And here's my result of different proportion of a tube. So for left one is about the different weights and the velocity. So in here I need to know the energy in here, so I use the kinetic energy to show the different relationship between the different proportion of the tube. And here's my comparison with my kinetic energy and strain energy, which also I use my theory to calculate it. So as you can see that the energy will have, despite the fact that it's not very similar, but it has the same trend that when the proportion of tube is become bigger, the energy will also become bigger too. So there is an energy loss between these two energies. So here's my comparison between my theory and my experiment. So as you can see that there's some difference energy between this strain energy and kinetic energy. So in here as video you can see that when I start to put the sketty into it, the debris of course will eject out, but also the original part of the sketty will also rebound to. So I think that there's the strain energy is staying in the original sketty. The energy won't totally transfer into the kinetic energy of the debris. And here's my conclusion. When about my mechanism between the sketty accelerator, I put a 2 point on the tube and also started pushing. And of course, it will cause a bending, and bending will cause a strain energy. And that's the debris will check out, turns into the kinetic energy of the debris. And here's my different relevant parameters in here. The first one is about enter weight. And I know that the stock on tube point is a more stable one than along the tube. And for enter velocity is different enter velocity of hand won't affect the strain energy and affect the frequency between the debris ejection. And my third one is about different diameter of sketty. So as you can see that with a 1.8 mm one is a much bigger moment of inertia, so it will have bigger strain energy stored, causing a bigger velocity of ejection. And for the first one is about different diameter of tube. I use a 12 mm diameter of tube has the fastest eject velocity of debris. For the fifth one is about the radius of tube. In here is that it have different result with a different diameter of the tube, shows that with bigger radius it has much less velocity of ejection. So I combine it together to see the portion of the tube and see that the 3 meter ones have the biggest velocity of ejection. So in here I can know that the radius of tube is much more important than the diameter of tube that will affect the velocity of ejection. And also in here, there's some condition that the debris won't eject out. The first one is about when I put the sketty along the tube, and the other one is the diameter of the tube, the proportion of the tube is bigger than 13 millimeters or less than 12 millimeters. The debris will eject out will stuck in the tube. And this is all my reports. Thanks for listening.
The opponent, you have 2 minutes for quick questions.
You use your hand to put the spaghetti into the tube, right?
Yep.
Okay. And can you turn to page 4? Is this picture on the left side about the breaking point? You want to explain it with the breaking point?
I collect the debris that I shoot out.
Okay.
Yeah.
And page 6. On the left side and the right side, the input angle is different, right?
Yeah. This one along tube and then the rest on the
And page 16. And you say that there's no energy loss, so it will totally transfer to the debris.
That's my assumption for this situation.
And page 18. Why didn't you use all type diameter of the spaghetti, not just tube?
Yeah, first in here I try to do a different diameter on the sketch.
Let's talk about it. 19. Can you ensure that your rope is in the right middle of the spaghetti? Because there will be some friction, I think.
I just put on the middle point.
But there might be some friction between it. Okay, that's
okay. Yeah.
22. You did different diameter of the tube, but did about the curvation? Like, I think your tube is not a perfect circle, right?
Do you mean the angle of this? It's just here just 90 degrees.
Yes, but the whole.
Maybe.
And opponent, you have 3 minutes to prepare later discussion.
可以帮我拿。
on.
Hello, I'm Yonglen from Timerico, and I'm the opponent of spaghetti generator. This is the problem recap, and they are mainly focused on the diameter of the spaghetti, and also like the size of the tube. Let's talk about report overview first, and about the observation and theory. They have a high-speed input to the tube, and they collect debris with the same length and assume that they have the same breaking points in the tube, and they use a 3D printer to print the tube. And there are experiments when the experiment and conclusion, they use tracker to analyze and use 3D, and they have qualitative explanation and initial. There are three phases, and the first one is initial, and the second one is buckling, and the third one is ejection. And they use spin theory to explain the velocity, and they use strain energy calculation to get stored, to know how many energy is stored in the initial debris, and how much energy is transferred into the kinetic energy. And they use different diameter of spaghetti. It's 1.8 millimeter and 1.5 to see the different velocity. Due to the different bending situation, assume they get different energy stored, and the bigger diameter cause the velocity is faster. And different, they also did the different experiments about the radius, and they discovered the same result as the tube. And they think the kinetic energy will be the same trend as when the proportion is bigger, the energy will be bigger. And energy, as they conclude, energy won't totally transfer into kinetic energy, and different enter velocity won't affect the energy. The things that they do great is that they use 3D printers for the tube, and also there are a lot of clear photos on the report, and he has a good translation and clear explanation about the theory. And also they use video to demonstrate the phenomena. And the things they can do better is that we think the rope is not in the middle of the spaghetti, but if you think so, you can prove to us on your slide. And the graph size, I think it's maybe too small, so we can't see it very clearly. And you didn't have like on your own theory and for this question, so you just like look something on the reference and like think it's related to this question, but you don't have like a whole theory. And that's all.
Okay. Please continue to the next page.
Okay, so first I want to talk about the input. Like you use your hand, right?
Yes.
So we think that's not very great because we think that the input velocity will cause the braking. What do you think?
Yeah, first I would consider this situation. So I also have to do some experience to talk about with a high enter speed and low enter speed, and this might result out here. So, but in here I think that maybe because the spaghetti will bend or break, right? But I think that when I put the enter speed, it depends on the critical strain of the spaghetti.
So how did you measure the speed of your hand?
No, I didn't have. Okay, that's fine. I didn't have exact number that how fast my hand is. I just very slowly, one by one, and very
Yes. So
yeah. So
you don't know what is the exactly velocity of your head, so you can't do this, right? I have a suggestion is that you can use like a machine, and there's a conveyor, and it is always be the same speed, and you can take the spaghetti on the conveyor, and so you can ensure that when you input the spaghetti, it always be the same speed.
Yeah, of course, I think that's a very great idea. So, for me, I use hand is also to make it more stable to control direction. But I think using the machine is a very good way too. So, I mean, I would consider
But
it.
how can you sure that your hand is stable?
Because
There's no vibration? Or?
in my intro, I said I put the scanning on the 2 points on the tube.
Yes, but I can also use put on 2 points of the tube with a machine.
Oh yeah, I'm not. I mean the putting machine using machine. I think it's very creative way, but I think my hands could also do. But of course, it's not better than the machine. So yeah, I think I would consider to use the machine.
Okay, so can you turn to page 18? Like as I mentioned before, why didn't you use all time? And I have another question: is that 1.5 millimeter and 1.8 millimeter is in the middle size of all your spaghetti, or what? Is smaller or bigger or something? Like what is the
Meaning of 1 point.
what is the other diameter of the spaghetti?
Oh, for this two one is 1.5, and the other 4 one is 1.8.
Oh, so you just did 2 diameter, but
Yeah, because they're just 2 different diameters.
okay, so you use different different brand of the spaghetti to test it, or you just use one brand?
One brand.
So why
It
didn't
gives
you do the other brand?
Because I measured young materials in here, and they're very similar, but my experience in here should change a different diameter. So yeah, I think I'll do the other brand.
And in this case, you have 2 parameters, right?
Can you tell me what's 2 brand?
Because you mentioned that you test the Young's modulus, and we can't make sure that different spaghetti from different brand will have the same. They use the same material to run them. So you change the material, and then you change the diameter.
Yeah, so of course the young material depends on the material. So in here I have measured 606 brands of young material. Here is very similar. But maybe I could show the exact young material in here. Yeah, so I think yeah.
Can you turn to the Young modulus page here? As I mentioned on the short question, the upper, the experiment. Yes, like as I see, I think the rope is not at just the right middle of the spaghetti, because usually you just put it in the middle. But how can you make sure that when you go to take a photo and it is still at the middle? You didn't like use a ruler or something.
Okay, maybe I didn't explain very well. So here I use some glue to stick it, so it won't fall down.
Yes, I know, but
yeah, I have used a red pen to dot the stuff on the middle point. So maybe it's not very accurate to show in this picture. Yeah.
yes, you got a round point on it, but you can make sure that when it's bending, it is still on the right point, because there are some friction between the rope and the spaghetti, right?
Yeah, I know. So you mean that when you push, because the spaghetti will bend,
Yes.
and so maybe the point will change.
Yes.
So I didn't consider this point, but yeah, I didn't consider friction between the rod, because here I want to see my different bending situation.
Yes, I think you did a great job on this experiment to know the Young's modulus, but you can do it better with.
Yeah, of course, I'll consider it.
And can you turn to page 25? Yes, and how did you measure the error bar?
Oh, I do 20 times for each different radius of centimeters.
Oh, yeah, that's great.
Okay,
22. You said that you did different diameter of the tube, right? And
yeah.
what I mean before is that is this a perfect circle for like 1 of 4?
Yeah, it is the same. Is a perfect cycle.
Oh, so you use 3D printer to
Yeah.
To bring the perfect circle and then cut.
Yeah.
Okay. And
But I think there's like I take a picture's angle maybe have some difference, so maybe it shows that not a perfect angle. Yes, yeah, but it's a perfect angle in my experience.
okay, then how about the curvation?
Can you tell me what the curvation?
Like, do you think that you change the angle of your square will change the?
You mean like a curvature?
Yes.
I didn't do this experiment, but I think that's very creative parameter to consider. And I think that with a smaller angle, like you mean like this, I cut it.
Yes.
Because when I cut too much angle, maybe the sketch will directly pass over.
Yes.
Yeah, so I think maybe it's some critical angle that sketch won't eject out to.
Okay, then you use a 2-point model, right? Like.
How I enter in 2 points.
Yes.
Oh yeah.
Do you think there might be a 3-point?
You mean like this point?
Yes.
In here, my 2 points is that you will keep contacting this point, but as you can see that this point was to keep moving forward. So I think it's not a fixed point. I didn't consider that as a third point.
So you ensure that you use your hand and they always attach to the, like this is the curve and this point and this point.
Yeah.
Right. Okay. And in your conclusion, you mentioned that there is some energy turned from potential energy to the kinetic energy from the bridge, right? And some will still stay in the initial spaghetti. So what do you think of the ratio of it? Like how much does the energy convey to?
Okay. So for this page, I have calculated out the energy transfer ratio. And so do you want me to say why the energy?
Can you explain it further?
You mean why it's different?
Yes.
Okay, so in here, can you play a video? Okay, so in the video you can see that I put a spaghetti in and degree project out. And for this part, our spaghetti will also slightly bend back too. So I think maybe there's some energy is inside, so it didn't transfer totally to the degrees.
So, where will the spaghetti like cause the degrees when it input to it? Where's the break point?
You mean the break point? I think it is this part, just this contact point in here.
So, like, is it like you have the whole spaghetti here, like
Yeah.
What is the ratio between here and here?
The ratio.
Yes.
I didn't calculate out it. Because I
So,
just calculated.
Where do you think that is?
You mean
Where? Like, according to all your experiments.
I think that is 2 parts.
Yes, I know it's 2 parts.
Yeah.
But can you give me
Okay. Sorry, can you tell more detail about the different ratio means?
like this is like 1 or this is how about this? It's 2 or 3 or 0.5?
You mean this part spaghetti and this part?
Yes.
I think it is 1 and 1. The ratio is this one. Yeah.
Okay. And do you think the input speed will influence the breakpoint?
The enter speed. Yeah.
Input speed.
Oh yeah, maybe.
Time is up. Now, opponent, 1 minute to summarize the discussion.
Okay, and here I want to talk about the summary. And they use hand, and that is not a great method. And I suggest that they need to use a machine hand. Different brand of spaghetti doesn't use the same. They use different brand of spaghetti, but just for the Young's modulus, but not further experiment. And the rope is not exactly in the middle of the spaghetti. They say there's a ground point, but they cannot make sure that it is just in the middle of the They say that their tube is from a perfect circle, and This is because the angle of the picture, and they think the breakpoint is in the middle of it, but I didn't do it, and I agree with this.
First, I want to ask for the reporter, and do you think the hand velocity is important to
No.
how about
I think the input speed is important because we didn't use that in this solution.
so you think the input speed is important?
Yes, it will change the next group.
Okay, and I want to ask the reporters, and how do you ensure the intergress are over the same?
Interwest.
You have the pull into the angle.
Oh, I just stuck on 3 points, so I can ensure that every time it's the same. But so the results also show that every time I shoot out the degrees of depth is always same. So I think maybe it's same, but I think I can prove it in my reports.
And the reporter, and do you think that the different size tube have the same friction?
You mean the friction? In here friction, I think it depends on the material that I use on the tube. So I think it's same.
And for reporter, and do you think that do you have major spaghetti are the same material? Because I think the Yamaha and if the different material will affect the Yamaha. So do you
Yes, because I can't ensure there's a same material. So I have measured 6 different best Yamaha shells and it's very similar.
So you have the different you have the different diameter of the spaghetti and the different material.
No, I think because like you said, the Yamaha shell depends on the material. Yeah, so I think that is change the moments of inertia in here.
Okay, and also do you think the glide will influence the energy calculation?
Yeah, because the spaghetti initially was just hit the tube first, so there is also some energy loss here.
How about you? Do you think the glide will influence the energy calculation?
Yes.
Do you think the different diameter of the tube have the same calculation?
Diameter one, I think no.
No.
Yeah. I think the radius
Why?
one, because the collection direction I think is more related between the different radius of the tube, because the different angle of the here, the different radius here.
So you think it's the angle?
It's not angle. I think it's more like the radius in here, because when I put in here, the different way that I put in have the same different ejections in the direction.
Time is up. Alrighty, for the review rate between here, for the review.
Hello everyone, I'm the reviewer and my name is Martin Chao and our team is the Crusaders and we are from the National Zhanghua Senior High School and today the topic I will review is the spaghetti accelerator. And the problem statement, when a piece of spaghetti is pushed into the bent tube and small debris of spaghetti may be ejected from the other end of the tube, expressing high speed and investigate the phenomena. And I think the focus is the speed and investigate its phenomena. And for overview for a reporter, and the phenomena is pushing spaghetti into and bent tube and it will eject in the breeze. And as the experiment is a various diameter of spaghetti and various diameter of tube and various radius and portion of tube. And the theory is in theory and I think and there are good setup and Tokyo theory and show the competitive theory and experiment well designed good time management. And we think that could have a more theory to improve that this phenomenon and could have used other way to push it to like the opponent suggests the machine and I think it will be the best way to control and also it can control one parameters. And for opponents, and it is clear to the problems of reporters and clear demonstrations of the report itself and adequate discussion on each problems. And also I think it has spent too much time and to have focused on the chart and PowerPoint could be clear. And the discussion and the opponent asks how to measure the force is in the middle and in the page maybe 18 and the reporter say he has to use a rapid points on the spaghetti and to show that it is in the middle and we think and maybe can more accurate the middle points. And also opponent asks if the tube is perfect cycles and also he says he uses a 3D printer to measure to cut in the 4 piece and to measure its perfect cycle. And also opponent asks about the push angle and maybe can use a machine and the reporter says it's a good suggestion and we think it's also a good way to control it. And we have as a hand velocity about hand velocity if it will affect the phenomena and opponents said yes they use machines and the reporter said maybe not important. And also we will have asked the different size of the spaghetti has seven versions and reporters tell us that the version is because of material so you would think it is great. And also we have asked the reporter how to show the two the intervals are the same and he said he used the 2 point to measure it will be the same point. And also we have asked about the collisions and I will ask the reporter and the opponent about the question will influence the energy calculations and also I said yes and we think it also yes and because I think the spaghetti
Reporter, 1 minute, 2 minutes for your concluding.
Okay, after having discussion with the opponent and the reviewer. So in my report, I have measured the different length of the debris. I also try to collect that and to see the difference between them. I also using I use my hand to input interview. So of course, like a reporter, like an opponent, I review the mirrors effect of it. So and also suggest me to use a machine. I think that's a very creative method to control the enter speed. And also enter angle. I put my sketching on the 2 point, so to make sure it won't keep shaking. So of course I can understand the opponent and reviewer, so maybe I can show it more clear on my reports. And I have used several parameters of different diameter, radius, and proportion. And also do have some presentation explaining of my different methods and also explain the bin theory. In here, I use my bin theory to calculate out how big the energy that when I bend the spaghetti that's stored. And because in here, I think the most important part is the energy transfer between the kinetic energy and the strain energy. And of course, I also have some reason of that the debris will inject. And for discussion with the opponent and reviewer, I think it's very great discussion and also excited about the different friction of measuring in the measuring young modulus way. So in here, I carry my way. I put a scan in the tube box and I fix this tube point. So the middle point won't change up and down. So maybe there's some presentation error in here. So thanks for opponents, I will show my best in the future. And also the shape of the cube to talk about different. It's not perfect circle or not, but in here I use a 3D printer to print it, and also the rate of energy transfer, because I think this is a very important point, and so say for opponent asking for the energy transfer, because it's a more key mechanism between this experiment. And this is all my remark for my reporting.
Thank you, Mel. Questions from the viewers?
I think maybe the main difference between we use hand or using tube. So can you, all of you, give us at least an order of magnitude estimate on how does this effect affect the final result? An order of magnitude estimate to use hand or tube to affect the final result.
Okay, first, okay, for me, I use my hand to do it, but I think the most point is about the critical breaking point of a spaghetti. So of course maybe there's some small effect of it, but the result shows that there's not a different when I change the other time parameters of this experiment.
Can you give the order of magnitude estimate?
Number?
Of my hand.
10%, 1%, 0.1%, or 100%. Order of magnitude estimate.
Sorry, estimate was.
The effect. How will this affect the final result?
I think maybe just like 5%. Yeah, I think it won't affect too much. I guess I don't extend number.
Yeah, how about you?
I think the N plus B will affect the max curvature of the spaghetti, and this is very important to the max curvature of the.
Please answer the question.
So
Order of magnitude estimate.
I think over 70%.
Over 70. So it's a very large discrepancy.
Very large.
How about you?
I think it can be 10%.
Really?
Yeah.
Why?
Because use the machine is can control the control is more clearly, but I think it is will have the gap between them, but it's not very too long.
I think so it's please.
I'd like you guys to comment on how to optimize these debris injection speed, and let's focus on the shape of this tube. The tube consists of a quarter of a circle and then two straight sections. So how do you optimize this shape to get a maximum speed? So what's your idea?
So I have changed the ranges and diameter, and for that, it's about proportion. And with a more smaller proportion, you will optimize the maximum speed of the debris, like a 3 millimeters one.
So we have a tube, right?
Right.
So you have a straight section and a border of circle and a straight section. Okay. So how do you optimize this debris speed by changing the shape of the tube? Because they affect this breaking point, they can affect the collision, they can affect this wave propagation and so on. So how do you optimize it?
It means to change how to change the speed.
Yeah, how to optimize the shape to get a maximum speed.
I think it will be the almost
almost maybe 85 degrees to this angle. So you will be the most deep.
He has mentioned that how to calculate the energy transfer in this report, so I think we can test the different radius and the different diameter and calculate the energy. So we change one parameter once a time so we can know that when will happens to max velocity.
Maybe one last question?
Please could you turn to page 41. And my question will go to all three groups. Please have your page 41 on screen. Okay, following Professor Wu's question, so my question goes to three groups. Given the data set here, do you really think the input speed matter? Yes or no? Given the data set. Input speed. Yeah, so input speed. Okay, so starting from the opponent, yes or no? Does the input speed really
I
matter?
can only use this data.
Yeah, data given here.
Oh, then that doesn't matter a lot.
Okay, and the reviewer? No?
No.
Okay. Okay. That's my question.
Thank you. Okay, so time is up. So now please, viewers, finalize the grades. Ready?
Yes.
Okay, good. So the score for the quarter. 5, 7, 8, 8, 7. And the score for the opponent. 5, 6, 5, 6, 7. Score for the reviewer. 5, 5, 6, 6, 6. Okay. Do I need to give comments? No, I don't, because I'm the lowest for the report.
You give comments.
May I give comments? Yeah. No. It's only for the highest or lowest.
Okay.
Yeah. Do we have this rule for this time? No, we don't have this rule for this time? Okay, so then maybe you can give comments in private. So
Yes.
Okay. Okay, so now let's conclude for this. We have how much time?
10 minutes.
Break? 15 or 10? We have 15? Yeah, 15 minutes break. Okay, but please come back after 10 minutes and if we can decide if we want to start earlier. Okay? In principle, we have 15-minute break. Yeah, but please come back after 10 and we decide.